Hello everyone, and welcome to another video where today I'm going to be showcasing a simple but pretty powerful feature that I've been working on today. During this morning, I haven't had much time to implement much stuff in Magicka lately because I've been busy with the stuff for class, but this is the thing that I've implemented. And you might be thinking to yourself, well, what the fuck is this, right? Like, what is this thing that I'm looking at right here? Well, this thing you're looking at right here within Magicka's code is two meshes, but within Blender it's one single mesh. So let me explain what is going on in here. What we have right here is one single mesh. Rather than it being separated as usually we have one crate mesh and one barrel mesh in here, I have merged these two together and I've modified a little bit. It looks a little bit ugly with that whole thing going on, but it was just for a test, right? And what you may have noticed is that now we have multiple materials assigned to single mesh, right? So as you can see, these two meshes are merged together and they are technically one single mesh, although they are, you know, separate parts, but that's beside the point. They don't need to be separate parts. They can be together, right? The point here is that there's two sets of materials that are assigned to this mesh right here. And this is basically a very simple implementation of a system to be able to export meshes with multiple materials. Before, right, I think I've already explained this before, but if we go over to my other map, we got it right here, I think is this one, yeah. So if we check this out, every single mesh that we have in this scene has a single material assigned to it, because before the exporter only supported one single material per mesh. It would pick the first material and it would be done with it, right? You know, that's okay. You can see how far I got with one single material for every single mesh. But there are some limitations when we try to get with more complex stuff, right? So the thing that I decided to do was finally go ahead and implement a system where we separate every single mesh into different parts and export those parts as different meshes so that we can support multiple materials, right? So the way that it's working right now, if we go over to the code, we've got a pretty big comment over here which contains what I'm going to be explaining in this video. But basically, during the get stage, we now have a function gsd add found mesh, right? And this function right here helps us add meshes to our found meshes list on the get stage of our program, right? What this does internally is that we go over to the mesh data, right? We get the mesh itself from the object in the Blender scene, and we say, okay, we're gonna take the number of materials, and if it's more, well, if it's 0 materials, we're gonna go ahead and just generate a list with a single entry, which in this case uses the number 69 because it's funny, but it can be literally any number greater than 0, okay? So I'll explain why. Basically, what we do is check how many materials there are, and if there are more than 0 materials, that is, the mesh has literally any materials assigned to it, we're going to generate an array, or a list in Python, right, which contains the value 0 for however many materials there are, right? And the point of this list right here is contain how many polygons use the material at every single index of the materials list, right? So for example, if we have a mesh with 2 materials, we will have a material at index 0 and another at index 1. And what we're doing with this list is generate a list with 2 positions, and every single index corresponds to whatever material index, and its contents is the number of polygons that uses said material index, right? And we go increasing this list by 1 for every single polygon that we find when we iterate over all of the polygons within the mesh, right? And we just increase it by 1 to know how many polygons it uses. And after that, we enumerate the polygon indices list, and we will just say, you know, we got the material index being the index itself at that position in the list, and the found is the number of found elements. And we don't care exactly about you know, the exact value of polygons that we found. We only care about the fact that we found at least one single polygon, right? And if there is at least one single polygon, we go ahead and we add this object to the list. What this means for us is that we're going to be adding every single mesh multiple times for every single material, as long as the material is being used on that mesh, right? What this means is that, well, we will have to process the mesh on the generate stage and the make stage multiple times, but we're doing this for greater performance in Magicka. So basically this means that when we go over to the generate stage, there's a simple check. Let me check def generate mesh data, right? Here we can see when we iterate over every single polygon in the mesh to generate the data, that if the material index is not the same as the input material index of this mesh, we simply continue. So that means that we are going to be ignoring this polygon on this mesh, right? So what this is going to be doing is that if we have a mesh on this scene that would have, for example, well, let's go ahead and paint this with some material that is green, right? We would be exporting a green material, and if we want to go ahead and paint this other surface with any other material, for example a red material, right, we would have ourselves one little mesh right here that has a set of faces that are painted with different materials, and before we did not support that. But what we do now is get this mesh, right, and check how many faces use the green material. Okay, these many faces. There's at least one face that uses this green material, so we're going to add this mesh to the list of found meshes. Now let's check the red material. There's at least one face that uses this. Let's add the same mesh yet again, and since meshes are referenced to a Blender Python object, they are pretty much just adding one pointer multiple times, so that's very lightweight, because on a system of a given width, it's basically adding whatever many bits there are for memory address. So in my case, I would be just adding a 64-bit pointer to the list every single time, and that's extremely cheap. It's just literally adding one integer, which is the reference to this object in Blender in memory, right? And then on the generate stage, we're basically doing the same thing as going over every single face, and we generate, for example, the material at index 0, we pick them up, and we are going to separate them. And that's literally what we're doing. We're picking the faces that have a given material index, we separate them, and we discard everything else, and this is all we're going to be generating. We're generating the green faces, right? And then when we get to the red faces, we do the inverse, and we discard everything else and only keep the red faces, right? And this basically means that we're going to generate every single mesh multiple times, but on every single generation step, we're only going to generate the polygons that correspond to every single material. So if we had a mesh that was one single cube in Blender, in Magicka is going to be exported as two different meshes with the polygons of every single material. So if we had another material, for example this polygon down here, or this one, you know, something disconnected somewhere else, right? For example, we could have a cube that was like this, right? So let me join this all again. So we got this cube right here, okay, and we could have this face right here be painted in red, and it's a disconnected part, right? And this is going to be very important. Basically, this whole thing would be its own mesh, even with disconnected faces, right? And this thing as well would be its own thing, even with this hole in here. And why is this important? Because Magicka does have a built-in system to do what we're doing in a different way. In Magicka, the meshes are represented in a different structure. They're represented with a binary tree, right? So this is my implementation in Magicka Pub for the level model reading that I created out of the reverse engineering process that I did for the level structure. And what we do have is a bi-tree model. This is basically a binary tree that contains information. The bi-tree model is basically a class that contains a list of roots and a list, right here we have the number of roots and a list of binary tree root nodes. And the binary tree root nodes basically have two children nodes, which are child A and child B. They contain more data. So let me explain. Basically, we go over to the root node, right? We contain all of the information about this level part, which is visible, casts shadows, sway, entity influence, the ground level, the number of vertices, the stride, the vertex declaration, the vertex buffer, and the index buffer, right? We contain all of this information right here, a material assigned to it, which is an effect. We got the number of primitives, which is the number of triangles, and the index in which this part starts, right? And that's very important. So, and we also contain the bounding box and has child A, has child B, and the child A and child B, which are binary tree nodes, right? So that means that the root node is basically the same. If we go over to binary tree node, you can see it's pretty much the same implementation as the binary tree node, only that the root nodes contain all of the information about the vertex buffer, right? The entire vertex buffer of the mesh is contained within each root node, and every single child node literally exists only to assign different parts for different purposes. So we've got right here number of primitives, start index, bounded box, etc. And this right here is a very inefficient system, right? We don't even have a way to assign different effects. As you can see, there's no readout for saying use a different effect here. Like, even if this could be used for this purpose, this is literally just trash, right? Because it's going to be causing a lot of memory segmentation. We're going to be fragmenting the memory a lot by having a binary tree structure for containing multiple child objects, when we could just have one single root object that contains the entire buffer for everything, right? And since the parent itself is the only one that can contain the effect anyways, we just go ahead and segment the mesh into two parts, right? So that we have a single continuous buffer, because due to the way that this is programmed, right, the binary tree nodes, they can only contain adjacent parts, because they require, you know, if you look at this, it has a start index and a number of primitives, which means that if we go to a start index in the vertex buffer, we can count only how many vertices we would consume to consume, for example, 30 polygons or whatever, right? And from that point onward, we would have to create yet another segment, right, for every single part. So even if this system has support for different materials, it would be far worse. So that's literally the reason why the binary tree structure is discarded, because it basically increments the memory usage pointlessly. Like, it makes no sense, absolutely no sense at all, to have this in the game, because I've made some tests, and every single map that I've made, even this very large map, which by the way, it's massive for Magicka standards if you think about it, right? I mean, not really, there are some very big maps in the base game, but this is pretty big, right? And if we use the binary tree structure, we would be consuming so much more memory despite having such a small thing going on, right? So the simplest solution for this is to literally just pick the mesh and segment it according to the materials that we have, and that's it, right? So yeah, that's all there really is to it for me to explain. Yeah, I could talk about something else. Another thing I've implemented is a system to apply modifiers. So this thing right here, you can see that it's a curve path that has a bunch of modifiers applied to it, an array modifier and a curve modifier, right? And these modifiers, you know, they would not be exported by Blender automatically, and you would just export the mesh as is without anything. So if we go over to mesh apply modifiers, there we go. basically we unified the process for mesh triangulation and applying modifiers, and now we have a get mesh data function which returns to us the mesh and the vmesh from Blender, right? And what we do is create a copy of the object. We're gonna link it to this scene, and then we go ahead, you know, we set it to active and we apply the modifiers, and then we triangulate the mesh, and then we remove the object from the scene and we unlink it. But since we're still referencing the mesh data, we're gonna make a copy of it and stuff, right? It's not going to delete this information. We could pass the mesh without copying it, right? And it would still work, but I prefer creating a copy just in case, because the garbage collector is not guaranteed to run after finishing our code. It could run at any point. So we could be referencing information that from Blender's point of view does not need to exist anymore, and this could lead to problems, although I'm pretty sure that Python's garbage collection system would prevent the mesh from being freed, because it's still being referenced. But since I am not sure if that is the case, because we don't know what Blender is doing on the C side and what Python is doing on the Python side, we're going to be pretty much better off just copying the mesh data and returning the copy, right? Because it's going to be freed automatically. The VM needs to be freed manually, though. I should probably add that. Node mesh is freed automatically. VM needs to be freed manually by the caller. Yep. I think I explained it in here. Yeah, they need to free VM manually. It's explaining here, but I'd rather add this in here again for clarity. So yeah, that's all there really is to be explaining here. So well, I think I already showcased it in a previous video, but basically, yeah, if we export now the map, this will be getting all of the modifiers applied. So basically, if you want to export a map using my tool with MagickCow, you don't have to do as much manual work as before, because before you will have to apply modifiers every time you want to export something by hand and separate every single mesh in different parts according to material if you wanted to export things with different materials. Now you don't have to do any of that stuff. You just need to go ahead and press the export button, and it's all done automatically. Now, one thing I would like to comment, by the way, is a problem that I came across at some point. When adding meshes from the asset library, which I will explain in a future video probably, right? We have multiple options for adding them, and it is many times ideal to add things through a reference, like appending by reusing data, or through append by creating new data. It depends on what you want to do with the object itself, right? But when we do that, we sometimes get a problem, which you can see here, which is we got duplicated materials because we already had those materials existing in game at some point, right? And I think some of this must be still referencing it because it's still in here. Before I had another material copy for the barrel, but now it's gone because we basically got rid of every single individual referencing that weird copy. But as you can see, we got this one, which is the name of our material, 0.001, because that's what Blender appends after it. So the thing I've been thinking about is that we should probably make a system where everything after the point will be ignored, right? So we just have this material with whatever name it has, and anything after the point will be ignored. So rather than making it so that this .json is the same as this, right, which is what happens right now, this gets appended .json after the end, we should probably just make it so that anything after the dot is ignored, right? So we start reading, and the moment we find any dots at all, we discard everything. So it will obviously fuck us up in the bad hole if we're considering the idea of allowing users to use points in their material names. So if your convention uses dots in the material names, you will have problems with this. You would have to go through underscores or whatever. Maybe that would be better. but at least it would prevent having problems in the case that people, when added a mesh, would accidentally generate a copy. So if I go ahead and drag this in here, you can see we got this 001 thing, right? Because since this is a new Blender session that I just opened up, is going to try to add this material with this name to the scene, since it's stored within the asset library itself, but it already existed on the scene. So what it does is just create a copy, right? And if I save and open this up again, it will yet again create a new one. So the only solution would be, if we don't do that, is go ahead and go through append reuse data, and even then you can see that since we already added stuff to this scene, it is not capable of recognizing that this material is the same as this material, so it cannot reuse the data, right? So and then we would have another problem, which is that these objects will become linked and you can make custom edits for certain parts. So you would have to, for example, make a copy and delete it to create a new unlinked object, or you could do it another way, which I don't remember, but if I recall correctly, you can go over here and you can press this button and it makes it its own user, right? It unlinks it, yeah. So those are problems of the way that Blender works. It's not really my fault, to be honest. I think so, at least. But if I do find a better way to make things work, I will tell you, because it would be ideal to have something. So I would like to hear your ideas on this matter. So I'll just keep going at it until I find whatever's best and most comfortable to play around with from the point of view of the user. So yeah, thanks for watching, and I'll see you in the next one.